More on deforming solids. Here we have three blocks. We could pull the block apart so it extends like this. We say that the block is under tension. We could squash the block like this and it would contract. We say the block is under compression. Or we could have forces acting along different lines like this, causing the block to twist, and this is a shear force. If the block is under tension, it is subjected to tensile stress. This is equal to the force applied divided by the cross-sectional area of the object. If it then extends, it will have tensile strain. This is equal to the change in length divided by the original length. If the object is squashed, it will be subjected to compressive stress. This is equal to the compressive force, the force squashing it, divided by the cross-sectional area. If it contracts, it will have compressive strain, which again is the change in length divided by the original length. The stress is given by this formula. The stress, be it tensile or compressive, is given the symbol sigma and is equal to the force applied divided by the area. The force is in newtons, the area in square meters, so the stress then comes out in newtons per square meter, but newtons per square meter are known as pascals. We can use this formula for the strain, be it tensile or compressive, where we use the symbol epsilon, is equal to the change in length, delta L, divided by the original length, L. In this case, delta L will be in meters, as will the length L, and therefore the strain epsilon is equal to a length divided by a length, which has no units. For tension and compression, the Young modulus is equal to the stress divided by the strain, and the Young modulus is given the symbol capital E, and so is equal to sigma over epsilon. The Young modulus then comes out in units of newtons per square meter or pascals, the same units as stress. Young modulus is a measure of the stiffness of a material. This is covered in more detail on the video entitled Young modulus. A material will generally have a different value of Young modulus in compression to its value in tension. Some materials, such as wood, will have different values of Young modulus in different directions. Wood is much stronger with the grain than across the grain. A steel cable is very strong under tension, but will easily buckle under compression. Concrete, however, is very strong under compression, but very weak under tension. Reinforced concrete combines these properties. It has steel rods embedded in concrete. So here we have a block of concrete, inside which are a couple of steel rods. The steel rods will give strength in tension. The concrete has strength in compression. When a wire is under tension beyond its elastic limit, it will eventually start to thin at the weakest point. This is called necking. So the wire gets longer and thinner. Eventually it thins at this point here. As it does so, the force remains the same, but the cross-sectional area of the wire at this point reduces. As stress is force divided by area, the stress increases at this point, and the wire will soon break. The strength of a material is its ability to withstand stress, and the breaking stress is the stress at which the material will fail. A brittle material will break with little deformation. A brittle material can be weak and break easily, like a biscuit for instance, but a material can be brittle and strong. Glass is a very brittle material, but it is also quite strong. What this means is it takes a large force to break, but there will be little deformation before it breaks. We want our biscuits to be brittle and break easily. If left out, they go soft and are less desirable. Here we have a brittle material. We increase the force on the material. It doesn't deform until it actually fails and the crack appears. Ductile materials display plastic deformation and can easily be drawn into a wire. Copper is a very ductile material, and this is how copper wires are made. So here we have a ductile material. We increase the force on it and it extends, becoming permanently deformed. Hard materials are difficult to dent or scratch. Hardness is usually tested by measuring the size of a dent caused by a diamond, being the hardest substance, which is forced into the surface. The end of a drill bit must be harder than the substance it is drilling into in order to make the hole. Here we have a diamond tip, and here a substance being tested for hardness. The diamond is forced into the material, and when it's removed, the harder the material is, the smaller the diameter of the dent will be. Malleable materials can easily be beaten or rolled into the desired shape. Gold is the most malleable material and can be rolled into extremely thin sheets, as used to gold plate items. So here we have a malleable material, and it can be rolled into a longer and thinner sheet. Tough materials withstand large impact forces without breaking. In a tough material, a lot of energy is needed for a crack to propagate through the material. Mild steel, as used in car bodies, is a tough material. In a crash, the body will bend and buckle, but often without fracture. Brittle materials are not tough. In a brittle material like glass, cracks propagate very easily. In fact, in a complete piece of glass there are stresses. As a fracture propagates, these stresses are released. The energy released by the stresses provides more than enough energy to extend the fracture. That's why a piece of breaking glass almost explodes. You would want the body of a tank to be a tough material, and so resist the impact of bullets. Composite materials combine the effects of two or more materials. Glass reinforced plastic, or GRP, which is also known as fiberglass, is a resin containing many thin glass fibers. The resin holds the fibers together and provides stiffness, and the fibers prevent the crack from propagating, making the material tough. GRP is used in boat hulls, canoes and so on, some car bodies, and the wind deflectors which are fitted to the cabs of lorries. There are also many other applications. Reinforced concrete, mentioned earlier in the video, is another example of a composite material.